Hello, in this video I'm going to be going through ferrous metals as it relates to preliminary engineering studies or Year 11 engineering studies. So it's worth noting that I'm using page numbers from Paul Copeland's Engineering Studies, The Definitive Guide, Volume 1. This is, I think, I'm using the second edition. We're now on the third edition, so these page numbers might not be the same as what you're using. And it's worth noting that I'm going to jump around. So I'm using this handout, and I'm going to show you the answer. The one with the answers is behind. But we're going to start by talking about carbon steel. We're going to talk about steel alloys. We're going to talk about stainless steel, and then we're going to talk about different forms of cast iron. So that's what these sheets have. So to start off with, we're going to talk about steel. Steel is a ferrous metal containing 0.1 to 0.2. You'll notice that's actually more accurate to say probably to about 1.4, but we'll say 0.2% carbon. It is a very important engineering material. Is allotropic, which means it exists in several crystal structure states, specifically austenite, ferrite, and cementite. So austenite exists as an FCC, facet and cubic. Ferrite exists as a body-centered cubic, and cementite, it has an unusual cubic, which we just try not to talk about. Now, austenite only exists at very high temperatures. It only exists when it's red hot. So if I look at my notes in here, so we've talked about this previously where we've looked at the iron-carbon diagram. And if we look at the full iron-carbon diagram, we can see that we have liquid up in these temperatures, up over 1100 degrees. We can see we have austenite existing at all of these temperatures, everything above 700 degrees though. So sometimes we'll have liquid and austenite, but we're mostly interested in this temperature range down here. So let's zoom in on that section, and we can see that we have austenite existing above 700. In the yellow section we have full austenite, but in the lower areas we have austenite plus something else. So this bottom line is called the lower critical temperature, and this line here is called the upper critical temperature. Above the upper critical temperature we're going to have full austenite. Below that, or in between those two temperatures, we're going to have some amount of austenite. Ferrite, pure ferrite, only exists at this range, in this little tiny orange area. So at very low carbon percentages and low temperatures. That's not to say that we don't get chunks of pure ferrite. That's why we have ferrite is represented by the Greek letter alpha, and we can see that we have alpha there. And even here, in this area, we're still going to have some, wherever we have pearlite, we're going to learn in a second that pearlite contains alpha. And the same thing here, pearlite contains some amount of cementite. So cementite exists in this half. Okay, so let's bring it back and let's find out about these things. So we said that austenite is an FCC. It only exists at high temperature. It can hold, I think, up to 2% carbon in its interstitial form. Ferrite, alpha steel, is a body-centered cubic. It is soft, ductile, and can only hold a tiny amount of interstitial carbon. Cementite, also known as iron carbide or Fe3C, is hard and brittle. Now that's relative. So when we say that ferrite is soft, it's soft compared to cementite. Cementite is hard compared to ferrite. Austenite, the properties of austenite we're not too concerned about because it doesn't exist at room temperature. Pearlite is a lamellar structure, which means it's in layers of ferrite and cementite. So if we have a look in this picture here, so it's named after mother of pearl, and so we can see those lines and mother of pearl. And what we're looking at is that often we'll just show it as a crisscross, but in actual fact, you can see here those layers. It's not a great picture, it's pretty zoomed in, but we can see those layers. Now, it's quickly worth mentioning that so what we're looking at here is ferrite and cementite, and it's worth pointing out that both of these are silver in color. What we can see is that when we clean this, we polish it up, and then we etch it with acid, and the acid cuts into the grain boundaries, so light gets trapped in that that etching, and it doesn't bounce off, and that's what we see, right? So none of it is black, none of it is white. It's what we can see, and what we can see is grain boundaries. So in the pearlite, what we can see is layers of ferrite and cementite, and in between here we can see this is big chunks of cementite. whereas here we have big chunks of ferrite. So we go back to our sheet. So pearlite is layers of cementite and ferrite. When austenite cools too quickly, the transformation from FCC to BCC doesn't occur because it cools too quickly. So instead it forms a body-centered tetragonal BCT. It's needle-like, which acicular is a fancy word for needle-like. It is very hard and very brittle, and it usually needs tempering in order to be used. Now, also it's worth mentioning that there is a ferrous metal with very low carbon content. That's called wrought iron, so you might need to know that. Wrought iron compared to cast iron, there's a question where I expect you to know that wrought iron has some amount of tensile strength. It doesn't cast particularly well. It can be forged. So those things are irrelevant to past HSC questions. Okay, so we can see a stylized version of pearlite here. You can see it doesn't obviously look exactly like real pearlite with that mother of pearl pattern, but it's fine. Diagrammatically, where you can draw, if they ask you to draw 0.83% carbon, then that's fine. Now, at 0.83% carbon, we get 100% pearlite. So we wouldn't have this layer in between. We just have 100% pearlite. And that's why on my diagram I have a zebra, so because it looks a bit like a zebra. It's really, and that's a picture of me because I'm born in 83, as is my wife, as is my cousin. So there are more Punzits born in 83 than any other. So to help us remember, there's a good video. The properties of grain structures is a good video that goes into a lot of this detail. You can look at that at some other point. Okay, back to the notes. So a acicular martensite, to draw a acicular martensite, we just draw it as lines, and if it's tempered, we still just draw it as lines. The video I just mentioned, it does a good description of talking about tempering and other heat treatments, but for the moment we can just say that acicular means needle-like, and we just draw a bunch of lines. Okay, so now we've got hypo and hyper-eutectoid. These are Greek words which mean more or less than eutectoid, eutectoid being where we have 100% steel. So if we go to this drawing, this picture, so where the eutectoid point can always be identified where there's a V. So this line here is where the V is. And then we can remember O is less than the V and ER is above the V. So we have hypo and hyper. Eutectoid means happy melting point. It's the low point, right? In this case, it's a bit of a misnomer, but we're going to stick with it. The Greeks never used that term ever. It's coined in the 19th century. So what we're going to talk about is low carbon and high carbon steel. So things that have more or less. Now you notice I've said high carbon steel. I've called it a hypoeutectoid. That's not really appropriate, but it filled the space. It's really either side. So we could say that high carbon steels are in fact eutectoid steels. But sue me. Don't sue me. No, I wouldn't like that. Okay, mild carbon steels, mild steels are just what we call them. Mild steels have 0.1 to 0.3% carbon. Remember, if it's less than 0.1, we call it wrought iron. If it's above that, we call it mild steel. And mild steel is the most commonly used steel. It's everywhere. We use it for beams, but it's also used for everywhere. Medium carbon is 3 to 6%, and it's used in axles. High carbon is 6 to 9, so around that eutectoid range, is used in saws. And tool steels are above eutectoid, and they are used in drills and things that punches, that sort of stuff. Now, you'll notice here that they've drawn the cementite in black. It's not black. I just want to point that out. Now, hypoeutectoid, they form big chunks of ferrite, whereas hypoeutectoids, what they do is they form channels of cementite in between the pearlite grains. So that's a way of drawing those things. Let me just show you an actual photo. So we've got hyper and hypo. Probably should have said hypo first. We usually go left to right. Hypo this is in fact mild steel with 0.3% and 1% hypoeutectoid steel. Okay, back to the notes. So now we've got steel alloys. Now, I don't think I've seen any questions on this. We kind of expect you to know that adding nickel and chrome improve corrosion resistance. We expect you to know that. But generally, I don't think you need to worry too much about these other things. So, it's in the syllabus. You probably do need to worry about it, but it doesn't come up all that often. Okay. If you add manganese, manganese improves toughness and hardenability. Now, manganese is used in a steel. What's that steel called? So I have a class that's the manganese class. I always use an element. I use this picture of a volt to represent it. So it's particularly hard to and Hadfield steel is what it's called, like the Hatfield and McCoys, except it's had with a D. Anyway, so that's where we use manganese. Improves toughness and hardenability. Sulfur improves machining. We said nickel and chrome both add corrosion resistance. Molybdenum improves hardenability, and we will talk about this next year when we talk about bikes. So it improves welding as well. So improve hardenability, strength, mild carbon steel at high temperatures. Vanadium improves strength and ductility at high temperatures. We really shouldn't use the word strength. We should specify what kind of strength. But I imagine I got these answers out of Copeland's textbook. So if you're going to sue someone, sue him. Anyway, tungsten, don't sue him. Improves strength at higher temperatures. So tungsten has the highest melting point of any metal, so that's why we use it, tungsten carbide, in drill tips and things. Copper improves corrosion resistance, but note that for aluminium, copper is bad. So it's good for steel, bad for copper. Good for steel, bad for aluminium. Silicon improves magnetic properties. Boron improves hardenability at low carbon content. Aluminium improves nitriding. So you might remember we talked about nitriding when we talked about hardening. Let me quickly show you that. So if we go here, we said surface hardening or case hardening. We have carburizing adds interstitial carbon into the surface, steel improving hardness. Nitriding is very similar to substitute nitrogen. This improves corrosion resistance, but it doesn't work over 500 degrees. So that's why we don't use it all the time. And titanium forms carbides, so that Fe3C. Also known as cementite. Okay, next we're going to look at the materials different kinds of stainless steel. So there's different kinds of stainless steel. I had a look. I don't think there are any HSC questions that have ever asked about these, but it's in the textbook, and it's in the syllabus, so we're going to talk about it. So there's ferritic stainless steel, martensitic, austenitic, duplex, and precipitation hardened stainless steels. That's what we are going to focus on today. So ferritic stainless steels are strong and ductile. They can be welded. Okay, and they're good for marine applications. Martensitic are not as strong, not as corrosion resistant. They're used in knives. Austenitic stainless steels are not magnetic. This is how you can have stainless steel implants in your body, and they're not magnetic. They can be TIG welded, but it's not easy. They're ductile and easily formed. It's the most common stainless steel. It can be hardened through heat treatment. And then we have duplex stainless steels, twice the strength, medium toughness. And when we say strength, we're probably talking about tensile strength. Medium toughness, a good resistance to stress corrosion. We will talk about corrosion in the end of year 11 when we're doing the HSC course. And then finally, we're going to talk about precipitation hardened stainless steels. So it's similar to austenitic, but with some extra materials. So niobium and tantalum. These are very rare elements, and they allow it to be precipitation hardened. So I took these green pictures. They're from the Year 12 textbook, so keep that in mind. But there's three steps to precipitation hardening. So first we're going to anneal, and then we're going to cool it slowly. Then we're going to condition, and that's the second step. And then we're going to cool again. And then later we're going to precipitation harden. And that's where we're going to leave it for a long time, also known as age harden. So the idea is initially what we're going to have is when we first cool it, what we're going to have is a mix of grains where we're going to have two different kinds of metal in forming in grains along the boundaries. And we don't really want that. It doesn't really improve its qualities. It doesn't give us the hardness that we want. So instead what we're going to do is we're going to heat it up again till we get a totally dissolved single phase, in this alpha phase. And then we're going to heat it up a second time, and this is called aging, or this is where the precipitates will form. And what we're going to have is very, very tiny, actually microscopic particles of the beta phase in between our alpha phase, and that's going to improve our hardness because it makes it harder to push dislocations through the grain structure. We will talk about this in a lot more detail in year 12. I have a lot of videos, and there's another engineering studies teacher who works in a school nearby. He's a metallurgist. He's got some good videos. Real Engineering has a video, but we really focus on aluminium rather than stainless steel. Okay, so what are the two steps? We've got our solution treatment, which is this conditioning, where we anneal and then cool before forming and fabrication, heat and condition to form austenite, then quench. So we quench, then aging, we partially reheat to promote precipitation formation, which strengthens the alloy. And for year 11, that is plenty of information. We don't need any more than that. So let's move on. Okay, cast iron. So what are the properties of cast iron? I always talk about how there's 2 to 4 things that you need to know about cast iron. The first is that it has 2 to 4% carbon. All right, so cast iron has a lot of carbon. I usually make a C with my hand when I say that. The next thing you need to know is it's got high compressive strength. It's good in compression, it is bad in tension. Right, so that's the second thing you need to know. Third and fourth things you need to know is that it has vibration dampening and can be easily machined, and that is because of the graphite that often forms when we create cast iron. We're going to see that when we get down. It's also got it's hard. It also is relatively cheap, and it casts well, so it can be cast into a variety of shapes, complex shapes, things that we couldn't form through forging or extrusion, that sort of stuff. Like engine blocks are the example we go to for cast iron. Okay, so when we add different elements, we get different properties. So first of all cast iron contains carbon, right? Like I said, the first thing in the 2 to 4 things is that it has a lot of carbon. So what does that carbon do? Well, it can either exist as cementite, and if it's cementite is hard. That is the property of cementite. It is hard. The second thing we need to know is that graphite improves machinability and dampening. That's things 3 and 4 we need to know about cast iron. So how do we make the graphite? Well, we make graphite using silicon. If we add silicon, it forms graphite in the cast iron, which we said improves machinability and dampening. Okay, we can add manganese. Manganese improves toughness and compressive strength. Sulfur is bad. We don't like it. It negatively affects the ductility. It makes it more brittle, and we want to reduce it. We want to keep it low. Phosphorus is good because it makes it flow better. So if you have fine corners or like very, very thin sections, you want to add phosphorus to improve flow. Okay, so let's have a look at these pictures. So typically, when we talk about cast iron, we can have white cast iron or grey cast iron. So the most common we have is grey. We've got 2 grey cast irons. Now you can see that what we've had here is we've got these big chunks of cementite, and we don't want big chunks of cementite. That's not really useful for us. What we instead can do is we can add silicon, and when we add silicon, what we're going to do is we're going to take out some of that carbon, right? And instead of having cementite, that high carbon allotrope, we're instead going to form graphite flakes. Now, if we have small graphite flakes, what we do is we still get pearlite. And if the graphite flakes get bigger, we're going to suck out even the cementite out of the pearlite. Because remember, there's still cementite in pearlite. We're going to suck out all the cementite until all we're left with is ferrite. So typically we talk about grey cast iron. When we snap grey cast iron, it looks grey, and the reason why it looks grey is because we have carbon in the form of graphite that we can see, and that makes it look grey. Now, that can either be pearlitic or ferritic. So let's have a look. White cast iron is generally, it's not very good. We don't really use it unless we need a lot of hardness, right? A lot of wear resistance. It's used to make malleable cast iron. So we're going to see that down below. Now, when I had an original video of this, I used a Dragon Ball metaphor, but I'm not going to waste anyone's time with that now. So we have pearlitic grey cast iron. Has high silicon, which makes graphite, which improves machinability and dampening. We're just hearing that over and over again. But what the impact is, it reduces tensile strength. And if we have ferritic grey cast iron, has excellent machinability and excellent ductility. So it's better still for those things. Because remember, the graphite, that's what graphite does. It makes it easier to machine, and the vibration dampening. And we've also talked about ductility because we know ferrite is more ductile than pearlite. Okay, then we have heavy-duty cast irons. There probably should be a hyphen there, but yeah, anyway. I'm not going to change it now. So we've got spheroidal and compacted. So spheroidal cast iron there's two different kinds of spheroidal, high and low carbon. It's that same concept. We either have pearlite or ferrite, depending on how much carbon we're absorbing. And so how we get spheroidal cast iron, we add magnesium. And what it does is gives us improved tensile strength. It's twice that of grey cast iron. It's commonly used in brakes. And we have compacted, this is over here, we have compacted graphite. So rather than being spheroids, it's more flattened. And we're adding magnesium and cerium and titanium. And it creates flakes, not as strong, but twice the vibration dampening as spheroidal grey cast iron, but still only half of grey cast iron. So that is the difference there for heavy duty cast irons. Malleable cast irons. So remember, to make malleable cast iron, we have to start with white cast iron first, right? So not grey. And what they have is the cementite is removed through heat treatment. They lose hardness. So remember, we started here with white cast iron with the cementite there. There's big cement chunks. And those cementite chunks are going to be removed. But we're going to go through heat treatment. They lose hardness, but have increased ductility and tensile strength. So we've got three forms. We've got black heart, white heart, and pearlitic malleable. So black heart, so we heat to this temperature, 900 degrees. It's about the same temperature for both, for all of these. And we're going to heat it for 48 hours, 2 days. And what we get is soft and ductile cast iron. It's used in suspension arms. Then, if we heat it for 100 hours, so that's for 4 days, we remove all of the cementite and the excess carbon dioxide. You'll notice there's no graphite here. It's all left. It's gone in the form of carbon dioxide. So we actually, oh, that's not what I wanted. It's in the carbon, this is used in pipes. Then we have pearlitic malleable, so it's got pearlite here and malleable cast iron. It's the same as black heart, but what we use is black heart cast iron, then we reheat it. So it's actually its third form. This is the Dragon Ball reference, right? So some villains have 3 forms that they well, I mean, guess Goku has like 6 forms, like as he goes through the different levels of Super Saiyan. Anyway, this thing has 3 forms. There's I'm just going to mention, so for classes they can look up the chicken nugget reference. But anyway, black heart cast iron, and then we reheat it again this forms pearlite. It has the highest strength of malleable cast irons, and it has good wear resistance, good hardness, and that is it. We are done. So just to reiterate, like what we need to learn about, I would say that the only thing that you really need to know out of all of this is, like when I say really need to know, if you want to focus your study, I would say as long as you know the first page, I'm happy. That's all you need to know for year 11. I would then also say that in year 12, we will need to understand precipitation hardening. If you learn this, you're exceeding my expectations, because if next year when I talk about precipitation hardening, you say, I remember that, we did that when we did stainless steel, I will be very happy. Other than that, cast iron is very low percentage. It doesn't come up very often in the HSC, and I only need you to know 2 to 4 things. So the 2 things you need to know is that it has a lot of carbon, 2 to 4% carbon. It has high compressive strength, but no tensile strength. And the other 3 things, 3 and 4, are vibration dampening and easily machined. If you know those things, I am very happy with that. So hopefully that was worthwhile.